So there's a lot of things there that when we first set out starting making this game, and we're targeting sort of an iPhone as a platform, that we sort of assumed would be impossible. And so we're going to talk about how to make those things possible. And that process starts, this approach starts with a line. And that line, it represents all the time and work that your game will be doing over the course of running. If we were to take that line and we were to sort it by unique work, we would end up with something like this, where over here on the left, we have things that, the handful of things that your game is only doing once. And over on the right, we have the handful of things that your game is doing every frame, but there's a lot of them because we're doing over and over and over and over and over again. And so this sort of, the talk focuses on sort of the frequency of things. And one of the sort of first optimization realizations that a new game programmer has, so there's a lot of things over here on the right, things happening every frame, that really don't need to be there on the right, that can be moved over towards the left. There's actually a huge benefit from doing that. I mean, if you assume that your game is going to be running at 30 frames per second for 10 minutes of gameplay, I mean, the increase that you have is huge. And as a programmer, we want to redistribute this work. We basically want to be doing something like this. The overall amount of work that the game does decreases, and this isn't like a micro level optimization thing. It's just making sure that the work we're doing is happening in the right place. The game runs faster as a result. And this is actually something that if you go to like the Unity forums or something like that, and you see someone who's making their first game ever, and they say, "Why is my game so slow?" This is like 90% of those cases. It's because they've written something like what's on the top, which is not only horribly inefficient, but rather pointless as well. But here in their update loop, they're just they're getting all the components and then processing. And they're basically told you need to cache things, and they end up with something like at the bottom, which doesn't do anything different at all, except that they don't have to, in every single frame, find every single component attached to this. I mean, it's sort of the very first optimization that any game programmer ever ends up doing.
So, can everyone hear me? Yep. Good. So if we take this and sort of go back and look at this, basically, any graphics programmer sort of knows this as well. Because if we take a look further down the time slot from a frame, we have stuff that happens to every vertex of your geometry and in every pixel. And again, you have these enormous orders of scale. And so I want to talk a bit about what this means when it comes to doing the shading of our game. And basically, when you need to make art look pretty, it's all about trade-offs. And normally in a game, pretty much all the shading happens at a pixel level. That is, if you make a Unity surface shader, that's where it'll be doing all its lifting, unless you sort of get clever and really sort of twist its arms. And it's very flexible, but the thing is, it gets super expensive when you have many lines, because you're rendering everything in the game for every line. Deferred shading gets a bit around this, but that's not going to work on a mobile device. So basically, So what you look at is like, there's no way this is gonna run on an iPad or an iPhone. So what most people do is they say, okay, fine, we're switching to vertex shading and sort of hoping that we can sort of do this loop because there's fewer vertices than pixels. And let's take a look at what that actually does to your visual quality. Like here we have sort of the game as we ended up making it, and it's basically switched into using only vertex lighting. And then it looks like this. And we see surfaces lose all that thing. This like nice metal part down here just became black. There's no detail on the bricks. So like, yeah, and if we switch back, you just see there's way more live, way more live. It just looks a hell of a lot nicer. A lot of this comes from the specular lighting, which you cannot do at vertex shading because it sort of flickers too much and it looks like crap. So basically, we have a problem here because it's like pixel lighting is too slow. Vertex lighting just looks horrible. And so we can't just shift the entire thing over. What we need is to sort of say, are there some parts of this rendering that we can shift over? So we sort of get a slightly better trade-off. So what if we said instead, we will shade on each pixel level, so we can do our bump mapping, we can do our specular, but we'll only calculate lighting per vertex. So we sort of rebalance this equation. And for that, we did hybrid lighting. Oh, that's a really nice and dark screenshot. What the hell? And the basic idea is that on every vertex in your scene, we figure out a single light that represents all the incoming light. So we have a yellow light over here and a purple over here. So we're sort of shading the vertex here. We'll sort of say we've got yellow, purple. Well, that's sort of a light that's halfway between color and pointing straight up. And then we run one pixel shaded light that we then bump map fully. And it's not accurate, but it's sort of, it works out okay. There's a ton of info on this. I'm not going to go too much into it on our blog. And yeah, take a look at that if you sort of want to dive into details. I think the main thing here is to sort of see that what made this possible is actually a rebalancing of the workload. So next we have, so like, why is this so much faster? And if we just run the math on this, it's pretty simple. On an iPad, we have about 4 million pixels on screen. Like, it has way better resolution than a console, and a way worse GPU. And then we have 250,000 vertices. And these days, graphics cards are equally fast, no matter where you put them. So any instruction I can move from the right to the left immediately becomes about 16 times as fast. And that's an enormous win. And like, I can optimize my lighting calculation like mad, but I'm not going to get a 16 times speeder. So I thought, yeah, this is nice. We've solved this. I showed this to our level designer. You can just throw in lights, blanketed in lights. And then we take a look at one of our levels here. And yeah, it's fairly large. And if we look at the lights, we have a few. And these are only some of the lights, because there's also some that are built programmatically, like anything that's sort of emissive in the game usually has a light source associated with it as well. So there's probably like 1.5 times as many. And the game ground to a halt. So let's go back to sort of this thing and say, can we do better? And well, we have to, obviously. So, and like the key thing is, like, as you know, when you're making graphics, most lights never actually change. There's some that do, you need to support those, but most of them are static. And so if we sort of expand our timeline out here to the right or to the left, then we introduce the authoring time. And the idea is to sort of switch some of the vertex stuff over to an authoring time. And this is pretty much exactly the same as light mapping, except instead of baking into texture, we bake into vertex colors. The interesting thing, though, is that this scene renders just fine in the editor. It's only on device we have an issue. So we don't have so we have like a 0.03 second bake time. So instead of like you have to bake a light map and wait for an hour, we can just do this every time in the editor. We hit play, or we go make a build. So from the graphics artist's perspective, there is no baking. But from like the player's perspective, we're good as far as performance are concerned. So that's the base idea. And to sort of ground it, I have a bit simpler example, which is our rain. And I sort of boosted in this screenshot, and then the ambient lighting in the room, I sort of removed it again. But hopefully you can see some like rainy stuff happening sort of there. And yeah, we wanted to have this wet sci-fi look, so we just needed rain. And basically, rain consists of two parts. You draw some lines on screen, and that's sort of the boring part. I'm not going to talk more about that. And then you want to draw splashes where the rain hits the ground. And you do that basically by shooting thousands of rays through the scene. And then anywhere it hits the ground or any other mesh, you add this sort of, or any geometry, you add a mesh which sort of contains a splash. And this is sort of the basics as I did it. At start, we shoot 10,000 rays, or we go through 10,000, find a random ray, see if it hits something, and then we just add it to the mesh. Real code looks a bit more convoluted than this, but you get the idea. Worked fine. Except when I tested on device, I had to wait for 15 seconds for it to shoot 10,000 rays against our entire scene. And we don't want players to wait 15 seconds for a level load, especially not on a mobile device. So basically we need to move all this over to the bake, and it's very simple to do that. Basically, Unity has this built-in function called scene post processors that not a lot of people know about. And any static function tag with this callbacks, this post-process scene, gets called when you hit play or when you make a bake. Any changes you make to the scene there are part of the scene when you're playing or in the final device build. So it's a bit different. We need to like find our rain object as a static function, but then we do the exact same. And now we have, again, like a quarter second when we hit play, but we have absolutely no time at startup. It's a bit of boilerplate code, and once you've written this 10 times, you get tired of it. So you sort of just make an interface, calls it normally, and it works. And here we sort of have like the actual code that calls the interface, and all the code for this is on our blog. But again, the key thing is move the computation to the left, so the player doesn't have to wait for it. And the nice thing about this is, once you've set it or just downloaded this code, there is no extra work for you involved, and your game just becomes faster.
I'm going to talk without the microphone too. I'm going to give another example of where baking works really well for us. And that example is to look at cover. And our game is effectively a tactical shooter. And so cover plays a pretty critical role, whether it's to, in combat, hiding behind the cover for protection, or whether you're sort of going from cover to cover, trying to sneak past guys. It plays a very critical role. And we have these sort of discrete cover points instead of sort of a continuous cover area. And the reason we do that is because, well, it's mostly it's input and movement resolution. Because it's a touch device and it's third person, conceivably your fingertip is the size of the crate that you're trying to hide behind. So what the game actually has to do is when you tap that crate, determine, well, okay, so I'm supposed to take cover behind there. Which cover is safe? Where did the player actually intend for me to go? So having reliable cover points to send someone to is sort of the strategy. But to have these reliable cover points, we actually need to know whether a single point is valid cover or not. And it's kind of a two-part question. The first part is, in the world geometry, is this a safe direction? Like, is there a wall here? Is this behind the crate? Is this a safe place to be? And then the other part is, if it's an exposed angle, is there an enemy there? And the first part of that functions a lot like the rain, because we need to just cast a bunch of rays out and determine how far to the nearest whatever we hit. In this case, we're looking at basically all non-dynamic stuff. And then the second part is if it's safe, is there an enemy there? And that has to happen at runtime necessarily because the enemies move around. If the enemy has line of sight to you, then that cover isn't valid, it doesn't protect you, you're not actually hiding, whatever. And we can actually make it so that line of sight calculation is really just a square distance check, because we can cast, when we determine the static geometry hit, we can just say, okay, well, what is the distance to the nearest obstruction? And then when we look at an enemy's position, we can just say, okay, well, are they closer than the nearest obstruction? If so, they can see the spot, and I'm in trouble. And so if we look at sort of these two tests, and they're generally where we want them because the really expensive one is these raycasts. This is sort of like a first implementation. It's happening in Unity on start. It's once when hitting play. And the test versus enemy, that's pretty fast. It happens a lot though, because it's basically the number of cover spots multiplied by the number of enemies conceivably. And that's happening over to the right, but it's a faster test. So when we manage to move, though, this test versus world over to bake, then it goes on this authoring side, and no player ever has to sit through all of these raycasts when they're playing. From their perspective, the cover is just working. But these hundreds of cover spots, and this is from a really small level. I actually had to choose our smallest level because to get the screenshot with all of the cover expanded, there's so many cover spots, it was incredibly slow lining that up. These hundreds of spots are still a problem. And not for the player because, well, they don't experience it. But it's a problem for us. We're three people. We're a small indie team. We're making this game. And there's a lot of cover. And manually placing all of this cover sort of while we're iterating through design so that we can sort of experience what a full combat area is just a lot of work. It's a lot of time that we really don't want to need to spend. So we actually sort of, since our whole philosophy is about moving work into the right place, what we can do is we can sort of introduce a new place for this, further to the left yet, and that's at import time, which means that we can basically take the asset post processor, implementing that, and do sort of the on pre and on post process calls. And it lets our artist in Max create a box, whether that box is on some art that's part of a tile or like a corner, or that art is like on a crate or something like that. Create a box, mark it as cover. In the pre-process step, we intercept. We say, this art is supposed to be covered. Anywhere it's used, we'll auto-generate cover there. And so suddenly we have a bunch of cover being just automatically generated. The downside to this is that we don't know anything about the scene at this time. So we actually need, you can see here, so this crate was marked as being cover on import. All crates in the game are. But it's generating spots that are inside of other cover once it's actually placed into the scene, because it could be placed anywhere in the scene. So we actually need to introduce a culling step into bake. And in that, we're going to just say, if one of these automatically generated spots is off of the nav mesh, if one of these automatically generated spots is inside of a wall, or if the artist flipped the cover on its side and now it's floating up in the air, we're just going to ignore that at the point where we're doing, when we start our raycasts to determine if cover is valid. And so the end result of this is that we've got sort of these three areas where work is occurring. We've got sort of at import, we're doing some work. We're sort of assigning what things are there, we're marking them up. At bake, we're doing the culling step where we're doing determining all the raycasts. And then every frame we're looking at whether or not enemies are legit enemies. And the sort of, if we look at sort of like how much time we're spending on each of these things, what we find is that the bulk of it's happening to the left, and that's really good. But the stuff that's happening every frame is actually still a problem. It's optimized, but checking against all of these enemies every single frame is still super problematic. It's dynamic stuff. We can't bake it. We can't move it any further to the left. Enemies can move. So what do? Well, we basically create a super simple load balancer so that we can say, if cover is not visible, I'm only willing to spend a certain, a fifth of a millisecond processing per frame with cover. And it's basically, we start a timer, we have a queue, we're popping off cover, we're processing the stuff that would have been in the update. And once it's processed, it's added to the engine. Once our timer's reached its limit, then we say, okay, well, we're done with cover for this frame. And that's fine, because nothing in our game is moving so fast that 30 times per second, it's validating and invalidating cover. Like that, we just don't need that frequency of update. So it's completely safe to say, yes, it's got to be dynamic, but let's move it as far to the left on this continuum as can sanely go. And this process, this creating this load balancer, opens up a new place on the timeline. And this is sort of these whenever things. We process them whenever we get around to them. It's still runtime, it's still happening repeatedly, but it's based on how much we can actually afford to allocate to whatever it is. I mean, all of our gameplay code is designed to be in just several milliseconds per frame. So we don't actually have a lot to allocate. So where do we use that? We use it pretty much everywhere. On the cover, as we said, agent behavior, our AI actually updates on a much slower tick. It doesn't need to make new decisions 30 times in every second. Same with senses. We can't avoid raycast there, but we don't need to send them out every frame. We can pull all of these things back. Our visibility checks, the actual thing that determines whether something's on screen that we have to iterate through all of the objects in the world for. Even with optimization to sort of avoid additional matrix math on the camera, it was still slow. So, but we really don't need to do it to everything all the time. Things just don't move that fast. So we really, this is something, this whenever step, pretty much if it's not a sort of player input, and if it's not something that's tied to animation and needs updates because it's on screen, then we basically don't need it to be updated nearly as frequently as the game itself is updated. Going back to cover, this is sort of what we end up with after making that change. We mark up assets, we column test the world. Off-screen enemies, we process whenever. On-screen, visible stuff, cover for those on-screen enemies, we process at a much faster rate. By moving, the actual implementation it required real optimization, but 90% of what we needed just happened by making sure that the work that we were doing at the right time and the right frequency, which is, if you're probably noticing, the theme of what we're talking about. There's one more thing with cover, though, that we wanted to do, and that's still involving cover and pathfinding. Because if you imagine that you have motion, someone needs to move from one side of the cover to the other. Let's say it's an enemy AI, and he's under threat from you. You're shooting at him from this direction. He's not going to take the cover. He wants to get to the other side of it. If he walks in front of the cover, he looks really stupid, because no sane person, when being attacked from one direction, would walk and put the thing that might block the bullets in between them and their attack. Like, we want him going around the side. On the other hand, if he's we want him going around this way. On the other hand, if he doesn't know you're there, if we can have him just walk around the other side of the cover, that sort of subtly communicates to the player that, hey, he's unaware that you're there, even though the AI knows that there's the threat exists in the world. Sort of his walking path, that he's not taking a defensive stance, actually communicates a lot. You know that you're still sneaking up. You know that whatever's happening. And so, trying to solve this, actually, it turns out that we have the tools to solve it already in our toolbox, and that's to use influence maps. We're already using them for our AI. We're already using them We're already using them for like camera control and a number of other things. And if you're not familiar with influence maps, I don't know. I mean, it's a pretty old technique. It was sort of old days of RTS development, decision making. I can actually, this is a video. So we've got the player moving through here. He's writing into basically a grid. And every frame, we're blurring that grid. And we've got an enemy up there, and he's writing into this grid too. And then we're able to make sort of decisions based on this. And in this case, the enemy can query this and determine sort of where the front line is. It's this blue band that runs through. The camera system looks at where the player has written in and knows how much it needs to pull towards the enemy to keep the enemy framed on screen based on where the enemy is in the player's influence map. We use this in all kinds of places to sort of make informed decisions about the context of the world. It makes sense that we could use it from pathfinding too, just so that you know how we're using. We have 15 after adding ones from the cover writing into them. We have 15 per level. It's a 1 by 1 meter grid that lines up with our tile system, so that we never have a case where a wall is partially on and we bleed influence through, or where we accidentally call. Propagation just goes into a double buffered byte array in another thread. So if you the double buffering is basically to make sure that we blur in a nice round way. And since it's a byte array, it's actually pretty small from a memory overhead standpoint, even at that relatively tight grid resolution. Dealing with the whenever aspect, though, becomes a little bit of a problem. Because normally you would want everyone writing into your influence map, and then you do the iteration stuff. But one frame, I might write in, and then immediately the next frame. But then it might be 5 frames before I'm called on by our load balancer to write again. And that's actually problematic from this. So what we do is we have another buffer, and the requirement for anyone writing into it is that before they write, if they've written before, they negate their previous value. And what this means is that this buffer can always be looked at as the latest from whenever things call. So if you twice a second, if cover is writing in, then it's always at any point in any frame that it gets pulled off to do diffusion. We have real actual data. And in our cover, what we do is we actually say, so each of these cover spots, when they do this sort of am I valid against enemies test, they write that value into the byte array. And then we diffuse that value around. And then our pathfinding can actually use that as a multiplier on its cost function. So we're able to effectively, from a pathing standpoint, warp space so that movement through safe cover is perceived as being shorter than movement that's not through. Or in the case, if we want someone to be exposed, we actually make that more expensive. We don't have to just use what we pull from cover from this. We could make, for example, a civilian that needs to walk through a level can look at the enemy and say, it's really expensive for me to walk through areas that are under enemy influence. And this is sort of using a fairly quickly implemented system to inform areas that we wouldn't normally think of using it or taking information from.
So yeah, in the graphics department, I'm the graphics programmer in case you can't tell. I want to talk a bit about how we do our reflections in the game. And I think the reflections were probably some of the first code we did, or at least that I did for this game. And we just loved how it works. So first I want to, and like how we actually make this run on a mobile device at a solid 30. So I just want to talk a bit about the various reflections that people are using these days. The first one is screen space reflections. It's all the rage currently. Has a few downsides, but largely it just works. It can reflect pretty much anything in anything else. It is a real next-gen technique. This is from Assassin's Creed 27 or whatever it is. And yeah, basically what it does is, when it needs to figure out what's the color of the reflection here, it sort of it samples the already rendered pixels sort of upwards, sort of saying, where do we hit something? So it traces every pixel against the screen. This also means that it's like super expensive per pixel. And yeah, there's no way this is going to happen. So that's sort of state of the art today. So a more commonly used one is the render the world upside down trick. It's ancient, and it works. Over on the left we have like a 4-year-old Unity demo, and on the left we've got GTA 5. And basically what we do is say, we know we have a reflection plane. If we have the camera beneath it and flip it, how does the world look like? And we render that into, we simplify the shading. This is kind of sort of get warped a bit. We use smaller render texture, smaller buffer. However, there's still many objects on here. There's like a ton of different geometry in the level. So there's quite a bit of pixel work which you actually need to render the scene. Quite often you need some sort of lighting to sort of match what you have. So a lot of vertex work, and there's quite a bit of sort of camera setup culling work every frame. It's a lot better than the other one, basically due to sort of the orders of magnitude of work here. But yeah, it's better, but it's still too slow. So then Sebastian Lagarde, when he was making Remember Me, came up with this technique of cube map reprojection. And basically, the idea is that we capture the finally rendered game scene into a cube map. That's sort of this probe that's placed. And an artist places these at like sensible locations. At runtime, at runtime, we reproject that out to simplify geometry that the artist builds. So then these walls can sort of basically be sort of a super low poly version of the world that's already been lit. And so it's a bit of pixel shader work just drawn that, but it's very, very little. And we tried that, and I was so happy, and I told graphic artists, now go make this. And basically what happened was that there was way too much manual work. He would keep on telling me, Nicholas, you need to fix the reflections. I would keep on saying, dude, you need to move your cube map a bit so it's no longer inside the crate you just placed, or you move the wall, you haven't moved this geometry. And baking these cube maps was still too slow for you to be able to just move something, hit play, test it. So, what to do? And this is, I think, it's sound like, just like shifting this work around, yeah, it's not enough sometimes. You need to actually sort of reconsider your approach to things. Let's take a look at how a screen actually looks in the game. But just filter out so we only have the reflections. This is sort of what we're seeing. And there's a few things that we sort of notice as we're doing this. One, reflections are super blurry. Two, lighting matters a lot. It almost matters more than the actual textures on the object. If something is lit by a really bright light, you need to see something bright in the reflections. Whether or not it's brick or stone might not matter. Also, the geometry has to match the rooms. And we have this wonderful tile map painting system, so the artist can super quick just mark out a room. If you need to expand an area, he can just do that. But yeah, we actually need to capture this. And so I came up with a solution. And now we also show sort of how where sort of the various work is doing. First thing is, at import time, just like you place something with cover, basically, you can place something with blocker. And essentially, the blockers are almost the same as the collision geometry we use. So it's just like giving the object, giving this box that encompasses the entire thing, the right name max, and it just works. So that gives sort of some import time work. It's a tiny bit of artist work, but he was already doing that for all the collision stuff. So at import time, what we do is that we render the real geometry into a texture atlas and reproject that onto the blocker. I have some images of that in a moment. So there, more import time, but that's okay. Like you import a crate maybe 20 times through the life of the project, and you hit play, I don't know, 50 times per day. So at bake time, we take all of these sort of really low-res crappy graphics, assemble them all into one mesh, and the nice thing about this is that this is just geometry at this point in the scene. We can light it just the same as we lit our world. And that creates some bake time work. But it's not too much. It's like, I think it's like, I don't know, 0.1 seconds every time you hit play. And then at render time, we basically draw this simplified world, which is just like one mesh. Maybe there's 5 different texture atlases. And it's a super simple shader. So it's just a tiny bit of pixel. So, and it's like, yeah, I tried it, and I want to start showing how this sort of, it feels like it shouldn't work, but for some reason it does. So basically, here we have a crate. At import time, we render it with no lighting from this direction. We also render it from the other direction, to the other faces, but that's irrelevant for now. And you shall see this is the texture we get. And it looks like total crap. However, once we light it, if we look at how the reflections of the objects actually look, yeah, it's kind of bossy up here. Yeah, looks okay. Over here, see the walls? It actually captures sort of the general shape of it. Maybe the resolution is even too high. So it's okay when reflections are super sharp. We don't actually render these reflections that sharp anywhere in the world. What we render is we blur them and sort of use the material properties. And now you can see, on my screen I can actually see this stuff down here. You can't on the projector, you'll have to take my word for it. But you see, it works. And if you look right at the top, you still see sort of get nice contact reflections from the sign. By the time we actually add the floors back in, then it's like, yeah, it works perfect. So, yeah, it works, and it's sort of, again, this sound like, okay, redistributing the work means we can actually do stuff like this on a mobile device, and it's not blowing our budget at all. So, to round off, here's an example. Do you want to?
Yeah, so if we take each of the sort of things that we've talked about and sort of naive implementations of them, we would end up with sort of a distribution of work like this. The brighter a dot, the more work is happening there. So if we look at like shading, we have most of the work in the pixel, a little bit in vertex. If we look at rain, most of it's happening still in runtime, but only once, which is nice. Some's happening in vertex. You can see where they fall. The interesting thing is what happens when we sort of do these changes that we talked about. Because we end up taking the bulk of the heavy work and pushing it so that players never experience it. Doesn't matter what device it's running on. And it's actually, I mean, our development machines are significantly faster than the computer, than a phone, right? Or an iPad. So like, it's happening now in the sort of appropriate place. And what's left are a few relatively dark dots that represent the sort of the work that the player experiences. And even those are biased a little bit more leftwards than they otherwise would have been.
Yeah.
So does it matter, all of this in the end? And I mean, I think our conclusion is that yes, it definitely does. Nick mentioned the sort of the 16x increase when we go from pixels to vertex because there are so many more pixels than vertices. But if we continue sort of that thinking across, we've got, well, there are way more frames in the course of, or way more vertices than there are single frame calculations. We move one step over to whenever this 3, that's, you know, it could be 10, it's whatever the update frequency that you can actually afford is, because we're moving into whenever time. And that's, like, the less optimized the rest of your code is, the bigger that number is going to be. And then, you know, obviously going to how long a play session is between objects needing to be loaded determines this. It's really not possible to determine the next step over what the performance gains are because the player never experiences this. But once we're on that side, moving something from bake over to import, I mean, there's 3 of us, we're 3-year development time, 3 of us pressing play 50 times. I don't actually, what was the math I did on this? I just wrote 3 people rebaking when they hit play. But we're hitting play every time. We import a model 10 times once it's been put into levels and things are changing. Like the overall increase in our time that gets freed up by moving things over to import is huge. So it's definitely worth it. And And it's not something that that requires additional effort. And I think that's, I mean, you guys are all going to be doing sort of game jam games in these next 4 years. You can, like, this doesn't require more work. It doesn't require more of your time. There's big wins with no additional effort. It's just about focusing on doing the right work at the right time. And that just, you know, if in doubt, just start as far to the left as possible. Just do things with the least frequency, and then if you can't get away with it, you know, move things over a little bit. And it's, you know, it's, yes, we have also spent a lot of time doing sort of real optimization in our game, but in reality, this is 90% of getting there. Yeah. I'm making that number up. This is
the best kind of numbers, my friend.
This is some
very politics.
This is some very high percentage of the work towards making, you know, in our case, run on mobile, but in any case, getting like fast performance and being able to implement features that otherwise you couldn't do on the hardware that you're targeting. And so hopefully it's something that over the next couple of days you guys are actually thinking about as you're doing this.
So yeah.
We have a dev blog. Almost everything we talked about, there's more in-depth stuff and there's actually code. You can also email either of us or tell us on Twitter, send us a message and say, hey, you didn't respond to my email. Thank you all very much for coming. And I think, we have a couple minutes, right?
Yeah, we have like, I guess, 3 minutes for questions, so
Yeah.
shoot away. Yeah.
Will the reflections work if you're able to rotate the camera?
Yeah.
Right.
Yeah, they actually just work. Like when we bake them, I sort of like walls, I know they don't get rotated, so I don't bake background stuff in.
Yeah.
And actually, the reflections are even better than what you normally have, because the reflections don't move, or the walls don't move, the floor doesn't move, so we can pre-reflect. We can actually reflect in different floor levels.
But say we're making another game where the camera could actually move around.
Yeah, it just works.
All right.
It also works in our scene view all the time. So yeah. Yeah?
So in the first example, after you optimize the game, I told the designer, go nuts, and you went nuts, and you have to optimize again.
Yeah.
So did that happen again and again?
Yeah.
And you just hit infinite, you're also
No?
You have
No.
to optimize again.
Now our issue is that we can only have a certain number of dynamic lights affecting every vertex. And that's the problem when you make a flamethrower.
Okay.
Right? I mean, you will always have a problem. Sometimes you say stop, and I think, well, I had taken a break from English, I think I figured out how to solve that problem last night. Right? So it never ends. You just keep on getting better.
Okay.
Yeah, and if you don't look at the stuff you did a year ago and think that was really stupid, then I've got some bad news for you.
For the gameplay things, did you ever encounter any problems moving things from every frame whenever? For example, not being able to click a cover spot or enemies moving funny because the pathfinding hadn't been updated?
No, and I guess that's so when the cover's on screen, so you can only click cover that you can see, right? So that once it's on screen, that's happening. But I guess it's possible because the visibility check itself is also happening whenever that there's like 1 or 2 frames where we've got old data, but it's old by like not very long at all. Yeah. Like it's old. I mean, when we're talking these timescales, we're talking about saving milliseconds in frames, not, you know, we never have 5-minute old data for cover anywhere. So no, the only thing that we do, because we have a sort of a time warping mechanic, the one thing that does require, because you can no longer just look at your delta time on frames, we actually need to store like a delta since I last got around to writing my thing so that we can know how long that's passed.
Anything else? Yeah.
Well, all that pre-baking, doesn't that come at cost of space or memory consumption?
Well, not really. Because like, if you need to, I mean, in theory, yes, you could sort of pre-bake too much. In practice, we haven't found this to be an issue. And like, I guess if you were targeting like an old Nokia crap phone, then you need to be super careful. In this day and age, like, you tell it any texture an artist makes is gonna just use up way more memory than anything else you have. So hasn't been an issue.
Well, I'm taking an example of some of the pre-baking on the graphics things. I mean, we're pre-baking things into vertex colors. So I mean, that's
Yeah.
data that was there. It's not.
I guess it normally wouldn't have vertex
Well,
color. So
but
you
it-
spend a bit, but like it's still like a fraction of a light map, right?
Yeah.
So yeah, usually it's worth it. Of course, if you want to make a full open world game, you probably don't want to load all your lighting information for the entire world, but like be sensible and it's not an issue. And you have more memory than you think these days.
Until you get to sound.
Until you get to sound. But we haven't solved that one.